Welcome to Spring LIB.
For part A of our question, we're asked to find the acceleration of the loop when the velocity is equal to 3 times 10 to the minus 2 meters per second. So an EMF induced in the left side of the bar because of the motion in the magnetic field. So this is the potential on the left side of the bar, which is given by the potential, we're just going to call it epsilon, is equal to the velocity of the bar times the strength of the magnetic field times the length of the bar, L. Okay, so from that, we can find the current, I, since it's equal to, according to Ohm's law, potential divided by resistance. Therefore, the force from the magnetic field B is equal to I times B times L, which is equal to V times B squared times L squared divided by R. Okay, so now that we know the force of the magnetic field, we can just use Newton's second law here, and we're going to have, we'll start a new page for this. We're going to have F external, which we were given, minus force of the magnetic field, F sub B, which we just found, is equal to mass times acceleration. Acceleration, of course, being what we're trying to find here. Acceleration then is equal to F external divided by the mass minus V times B squared times L squared divided by the mass times the resistance. So plugging all those values into the equation, we find that the acceleration is equal to 4.14 meters per second squared. We can box that in as our solution for part A. Part B asks us to find the terminal velocity and the acceleration when the velocity is terminal. Well, since the terminal velocity is the velocity at which it can accelerate no more, the acceleration there a priori is known to be equal to 0. So right away we know that's true. A sub t for terminal is 0. Okay, so the terminal velocity happens when the external force is equal to the magnetic force. Therefore, this is equal to V terminal times B squared times L squared divided by the resistance. So solving for the terminal velocity, we find that this is equal to F external multiplied by the resistance divided by divided by B squared multiplied by L squared. Plugging those values into this expression, we find that this is equal to 0.069, 669. And then units here are meters per second. We can box this in as the second part of the solution for part B. Okay, now part C asks us to find the acceleration of the loop when it is completely out of the magnetic field. Well, the acceleration from the loop then, when it's completely out of the magnetic field, is going to be the external acceleration. So F equals ma. So ma is equal to F external, right? Therefore, A is equal to F external divided by m. Well, F external divided by m comes out to be 7.50 meters per second squared. We can go ahead and box that in as our solution.